Hello, this is a Laplace transform question from May 2017. It's in 3 parts. Part A, show where L is the Laplace operator that the Laplace transform of e to the minus at is equal to 1 over s plus a. That's worth 5 marks. Part B is determine the inverse Laplace transform, because that's an L to the minus 1 there, of this function here, s minus 1 over s squared minus 2s plus 3, using information in the attached transform tables. And the third part, solve the first order initial value problem, dx dt minus 6x equals 2, where x of 0 equals 2, using the Laplace transform tables, and that's worth 14 marks. So they're all based on this idea of the transform. Okay, so part 1 is if you have a Laplace or a function, f of t, a time-based function, and you do a Laplace transform on it, you get this function, capital F of s. And part A, is asking to do that, the Laplace transform. And this Laplace transform is generally integration between 0 and infinity of e to the minus s of t times the function dt. But then part 2 is asking us for the inverse Laplace transform. It's asking to go this way, from capital F of s to little f of t. And they require use of the tables. Right? So these are the Laplace transform tables. You're not given the top 2 rows here. They're just I just thrown them in. Anyway, so this here is the function on the left hand side, and on the right hand side, this is the result of doing a Laplace transform on the function, i.e. integrating the function between 0 and infinity multiplied by e to the minus at dt. So the first one he asked for was to find the Laplace transform of e to the minus at. Well, there is e to the minus at on the transform tables. That's a function, and then when we do a Laplace transform on it, we should get 1 over s plus a. And we have to do that integration and get 1 over s plus a. The second part is saying that there is a function somewhere here on the right hand side of the tables, and we have to do an inverse Laplace transform and find out what that function was originally. It's like the backwards version of a Laplace. Okay. Part 3 we'll get to when we get to it. So now part 1. Show that the Laplace transform of e to the minus at is equal to 1 over s plus a. So we have a function f of t which is equal to e to the minus at. And if we have to do a Laplace transform on that function f of t, we have to integrate between 0 and infinity e to the minus st times that function dt. That is your standard Laplace integration. Okay, so in this case f of t is e to the minus at. So we put that in. So it now becomes, so the integration, the Laplace transform of e to the minus at becomes the integration between 0 and infinity of e to the minus st times e to the minus at, this is the ft, there, dt. To do an integration, sometimes you just have to rearrange this so it looks like something that's easy to integrate. So we can, if we use the exponentials, that e to the a times e to the b is equal to e to the a plus b. This little rule here will help us with this. So we can now say that the Laplace transform will become Laplace transform of e to the minus at can now become the integration between 0 and infinity of e to the minus st minus at dt. We've just put them together, like here. But it still looks a wee bit weird. We have to integrate this with respect to t. So we could take t, and in fact we could take minus t out as a common factor and tidy this top part up, and it will make it easier to integrate. So it's the integration between 0 and infinity of e to the minus t on s plus a dt. You might wonder, why is that a plus a? But remember, you have to multiply it by the minus, so minus ts and then minus t times a. So it works back to this. So now we just use the basic rules of integration. Now some of the basic rules of integration are if you have to integrate between, say, forget about the integral for now, if you have to integrate e to the x dx, your answer is e to the x plus c. That's in the tables. If you have to integrate e to the 7x dx, your answer is e to the 7x over 7 plus c. If you have to integrate e to the minus 4x dx, the answer will be e to the minus 4x divided by minus 4 plus c. This one you have to be careful about because of the minus sign. This can be written as minus e to the minus 4x over 4 plus c. Okay, so now then let's get back to the integration. So we have to integrate this. And this here, s plus a, is basically equivalent to the 4 in this one. So it will now become, if we integrated e to the minus t on s plus a, still stays the same, over minus s plus a, and rather than have a plus c, we have our limits. Now s plus a has nothing to do with t, so we can take that out. That's 1 over s plus a on minus e to the minus t on s plus a. That minus is from there, between 0 and infinity. Now it's worth thinking that if t was infinity here, that would overwhelm the s plus a. So basically it would be like e to the minus infinity. So if we had something like e to the minus a very large number, just call it any large number like this, but this number is getting bigger and bigger. Remember, that's 1 over e to the power of a. If a is getting really, really large, this number is getting really, really large, but this fraction overall is tending to 0. So the limit as a tends to infinity for this is equal to 0. So if you can just remember e to the minus st as t tends to infinity becomes 0. E to the minus st as t tends to infinity becomes 0. So if you put infinity in there, that's going to be 0. Now if you put 0 in there, that will be e to the power of 0. But e to the power of 0 is the same as anything to the power of 0. It's equal to 1. So this will now become 1 over s plus a on minus 0 minus minus 1, which becomes 1 over s plus a on 1, which is just 1 over s plus a, and that's part A proved. Okay, then part B. Right, determine the inverse Laplace transform of this. Now the problem with this is if you look at the tables, there is nothing in the tables that looks like that. Okay, so we have to rearrange this, especially the bottom part, to try to make it look like something like this. And I can tell you it's going to look like one of these things here. Right, so let's try that. So first of all, I want this to look like some sort of square underneath. So we'll take the bottom part and consider s squared minus 2s plus 3. And we have to change it some ways. So what you do is look at the square. You take this number here that's in front of the s, and you divide it by 2. So if that had been a 6 minus 6s, we would say it's minus 3. In this case it's minus 2s, so we go with s minus 1 squared. And that becomes s minus 1 times s minus 1, which is s squared minus s plus 1, which tallies to s squared minus 2s plus 1. So see, we still have an s squared term and the minus 2s. The only difference here is the number. If we were to add 2 more onto this, it would be the same as that. So if we were to add 2 more onto this, it would be the same as that. So s minus 1 squared plus 2 is equal to this, s squared minus 2s plus 1 plus 2, which is now equal to s squared minus 2s plus 3, the same as here. So now we have transformed the bottom. Well, we haven't transferred the bottom. We've just rearranged it algebraically to make it look like the bottom of this. Now, the reason we go for that is because here in the tables we have this s plus a squared plus b squared underneath. That's what we have, where our a is minus 1. So we will make this look like s minus 1 squared plus 2, and we want to make it look like s plus a squared plus b squared. The only problem is this is a 2, it's not a squared. But if you think about it, the square root of 2 squared equals 2. So we could rewrite this as s minus 1 squared plus the square root of 2 all squared. So we could say, well then a must equal minus 1 and b is equal to the square root of 2. That's great. We've got the bottom part sorted out, but we still have to look at the top. So now what we've got is s minus 1 over s squared minus 2s plus 3. Now it looks like s minus 1 over s minus 1 squared plus the square root of 2 squared. But this is like s plus a over s plus a plus b squared from the tables, right? S plus a over s plus a squared plus b squared. If you check the tables for this one, s plus a over s plus a squared plus b squared is on the left hand side, and on the right hand side we have e to the minus at cos bt. So we have e to the minus at cosine bt, and then if we did the Laplace on it, it would be equal to s plus a over s plus a squared plus b squared. And we have identified that for our function here, a is minus 1, and b is the square root of 2. So when we do the Laplace transform on that, it goes to this. But we're doing the inverse Laplace transform. So if we do the inverse Laplace transform on this, we will get e to the minus 1t times cosine the square root of 2, which is the b, times t. And we can tidy that up as e to the t cosine root 2t. So we were asked for the inverse Laplace transform of this, which from the tables is going from the right side to the left side, and that gives us this, and that's the answer. Okay, so now we're on to part 3, or part C. So part C is quite a long part. You have to solve this first order differential equation. A couple of things I'd like to say. First of all, that x is actually a function of t, so it can be written as x of t. This could be written as d on dt of x of t minus 6x of t equals 2. And this x of t, in the transform tables, it's represented by f of t on the transform tables. Another thing about it with the transform tables, the dx of t dt can be written as x dash t. And in this case, this dx dt up here is actually x dash t. Now there is no x dash t in the transform tables, but there is f dash t. There. Okay? So wherever we see the f dash t, we use our x dash t. So there are 3 steps to this question. 3, a lot more in the third step though. Step 1 is do a Laplace transform on every term. Okay. Step 2, isolate x of s. Get x of s on its own. And step 3, do an inverse Laplace transform. On x of s. So basically what we do is, when we do the Laplace transform, somewhere in the equation we will have we had little x's of t's, and they will become capital X of s whenever we transform them. But if you do a inverse Laplace transform on x of s, you will get little x of t. Basically, because if you do a Laplace transform on x of t, you will get capital X of s, and if you do it the other way around, you will get little x of t. Okay, so part 1 then, or step 1, let's Laplace the whole equation. So rather than call this x dx dt, I'm going to call it x dash t. So we have to do a Laplace transform on x dash t minus 6 times the Laplace transform on x of t equals the Laplace transform on 2. Okay, so these you have to go straight to the tables, right? Okay, so according to the tables, the Laplace transform on f dash t is this. I'll write that down. So in the tables we have f dash t, we do a Laplace transform on it, and we will get little s capital F of s minus little f of 0. Right? So if it was a Laplace transform of little x dash t, which is what we have, it will be s capital X of s minus little x of 0. The next part is the Laplace transform of x of t. It's not really in the tables. It would be f of t and it would be this, but that could be called capital F of s. So if you have a Laplace transform on little x of t, it is capital X of s. And the last part from the tables that you need to know is the Laplace transform of 2. That is a. A is like for any ordinary number, any number. So if you do a Laplace transform on a, you get a over s. So if we do a Laplace transform on 2, you will get 2 over s. So what we have to do now is put these values here into this equation. Let's try that now. So it's the Laplace transform of x dash t. That's this. So Laplace transform of x dash t minus 6 times the Laplace transform of x of t equals the Laplace transform of 2. From the tables we can now write that this is s capital X of s minus little x of 0 for the x dashed. Then minus 6 capital X of s equals 2 over s. That's step 1 done. Now step 2, we have to isolate x of s. That means we take this out. We can change this because the initial conditions were that x of 0 equals 2. So we can put that into this equation. That's a start in tidying it up. So we'll have s x of s minus 2 minus 6 x of s equals 2 over s. Take this x of s out, bring the minus 2 to that side. So we'll bring the minus 2 over first. S x of s minus 6 x of s equals 2 over s plus 2. Right. So we take the x of s out of these two, it's the common factor. X of s out, and we're left with s minus 6 equals, for this side here we should get a common denominator, and we could get s as a common denominator. If we multiply this 2 by s above and s below the line, really we haven't changed it because s over s is 1, So, but we still have a common denominator now. So that now becomes 2 over s plus 2s over s. So now we have a common denominator of s, and we have 2 plus 2s. So now all we do is bring the s minus 6 underneath here. So we have x of s equals 2 plus 2s over s on s minus 6. Right, so the next part here is to use partial fractions. That's what makes this part a little bit longer. Okay, this can be written then as, the reason we use partial fractions is we can use something like this. If we get it something like this, we can work backwards. It's easier to work from. So that will become a over the factor s plus b over the factor s minus 6. Now this is the equation we're working with. If we multiply everything across by s times s minus 6, we will have 2 plus 2s over s on s minus 6 multiplied by s on s minus 6 equals a times s on s minus 6 over s plus b on s minus 6 over s minus 6. And we get cancellations. All of that cancels with all of that. And we're left with 2 plus 2s equals, the s's cancel here, a times s minus 6 plus the s minus 6 is cancelled here, b times s. So all we have to do is find a and b. To do this, I could say, first of all, let s equal 0. That would eliminate the b. So let s equal 0. And we will have 2 plus nothing equals minus 6a plus nothing. So that means a must equal 2 over minus 6, or minus 1/3. And then to get b, if I let s equal 6, that will become 0. A will be eliminated, so let s equal 6. We'll have 2 plus 2 6's are 12 equals 0 plus 6b. 14 equals 6b. b equals 14 over 6, which can be written as 7 over 3. So now we go back to the original of this here by parts equation, or partial fractions equation, and put in a and b. So we now have that 2 plus 2s over s on s minus 6, which is equal to x of s, is now equal to a minus 1/3 over s plus b 7 over 3 over s minus 6. And now we have it in a stage that we can use the transform tables. So now step 3, this is step 3 actually. No, this is step 3 now. Do an inverse Laplace. So if we do L to the minus 1 of x of s, that means L to the minus 1 of 2 plus 2s over s on s minus 6, which is minus 1/3, bring that outside, on L to the minus 1 of 1 over s, plus 7 over 3 on L to the minus 1 on 1 over s plus 6. So now finally we have a look at the tables, and we can see that 1 over s on the tables would be a over s, which will give us a, which is just 1. So if we do that, that just becomes 1, and that becomes just minus 1/3, plus 7 over 3, and if we do the inverse Laplace on 1 over s minus 6, that's that one. So on the tables, so for this one here, do it up here, on the tables we have 1 over s plus a on the Laplace side, and on the function side we have e to the minus at. So if it's 1 over s minus 6, that is going to be e to the minus 6t. Yes, that will become a plus. Minus minus. So we now have that the inverse Laplace function of the original question, which was, the inverse Laplace of x of s is equal to 7 over 3 e to the 6t minus 1/3. That is actually now x of t, because when you do the inverse Laplace of x of s, you get x of t. So this is the solution. X of t is equal to 7 over 3 e to the 6t minus 1/3. That's the end of the question, but really, if you want it, you probably don't, but if you do want, you could check it. So if we go back to the original formula in the question was here, dx dt, x dt minus 6x equals 2. So let's just put in the value we get for x of t and see if that works out. So basically it's d on dt of 7 over 3 e to the 6t minus 1/3 minus 6 on 7 over 3 e to the 6t minus 1/3. And that should equal 2. So if we differentiate this is differentiation now, it will become e to the 6t 6 times 7 over 3 minus the third goes, so that we're going to differentiate it, so then it's minus 6 times 7 over 3 e to the 6t minus times minus plus 6 times a third, 6 over 3. They cancel out and 6 over 3 equals 2. Therefore, this is the solution to that. Thank you.